you so much for the EASF team for this wonderful webinar series. I think it's a great opportunity for young scholars and early career researchers. So thank you for that. So today I'll be talking about design of novel magnesium alloys for extreme dynamic environments. I did my bachelor's in mechanical engineering and my MS and PhD in material science. So a lot of my work is at the intersection of material science and mechanics. And today it'll be a little bit more material science focused, but the emphasis is on for and rather than in, and you'll soon know why that is. Every talk I often dedicate it to a research scientist that I really like, and I would like to dedicate this talk to James Rice. I was really, impressed with some of his writings, and one of the things I recently came across was the solid mechanics document, where he talks about the difference between a solid and a fluid, and talks about the importance of shearing deformation. And you'll soon see in my talk how important that is. So with that, I would like to sort of briefly show you the framework of my talk, and I'll go through this as I deliver my talk so that you know when the end is near. Okay, so first I want to kind of talk about why extreme dynamic environments and what are they. So here's an example of a soldier injured in a battlefield. You can see his fingers are injured, the armor plate is damaged as well. This likely happened because there were particles or shrapnels flying at a very high speed that impacted the soldier, right? Here's another example from space, a satellite system that's damaged by space debris, again, moving at a very high speed, hitting this satellite system and damaging it. This actually is from a Tesla car, as you can see here, that was damaged in a car collision, right? So in all of these cases, sort of an impact event led to either people or systems in danger, right? So that's what extreme dynamic environments are. And obviously, it's important for us to sort of study some of these events, but also develop new materials for these dynamic events. So I want to take you to a little bit more, give you a little bit more insights about this extreme dynamic environments. So obviously, we are depositing a large amount of energy over very small amounts of time. You can see here's an example of a small spherical ball hitting a plate at a very high speed, right? But if you think about the speeds for the energy to propagate from a material point, it's finite. So think about wave speed or crack speed, right? So the system, the material system seeks new internal pathways to dissipate that energy. And every material has a spectrum of available pathways. So what I call as available mechanisms. For example, if it's a ceramic plate versus a metallic plate, or maybe some kind of a composite, they're all going to have different sets of mechanisms through which they dissipate this particular energy, right? But through material science, we can actually control the microstructure of the materials in the hope that we can tune these mechanisms, right? And ultimately control the performance of materials. And if you think about it in that perspective, right, you can really control the microstructure across length scales and really think about this in a sort of a hierarchical design perspective. There are length scales to think about, there are time scales to think about, and that really opens up a vast array of sort of design at the intersection of material science and mechanics. And that's a snippet of it is what is going to be focused in my talk, right? Another thing that one has to think about when you're thinking about materials for extreme dynamic environments in particular is the benefit of having lightweight materials, right? So here's an example of a soldier with all the protection materials. And if you look at the sort of the cumulative weight, it's almost around 27 pounds, right? And when you're on the battlefield and you're fatigued, every pound matters. And a big question for protection materials, whether it's body armor or vehicle armor, is how do we bring this weight down while still protecting people or systems in the battlefield, right? But it's not only for defense. If you think about various other applications like aerospace or automobiles, lightweight materials that are very strong across strain rate regimes, across maybe even temperature regimes or pressure regimes, are very, very useful. So the sort of conclusion here is that the lightweight materials are critical for extreme dynamic environments and have a lot of advantages. So if you really go in search of these lightweight and strong materials, there are certainly a lot of materials to consider. I work a lot with metals, and if you think about all the metals that are out there, especially available, commercially available and abundantly available, you can look at a couple of them, especially lightweight metallic alloys, and it quickly becomes obvious that magnesium alloys are quite favorable, right? They're around 35% less dense than aluminum, so they're very attractive. But there's a question mark here. Why? It's very well known that they are very lightweight, but can we make them strong? That's the whole question. So there are two big challenges, I would say, in trying to design magnesium alloys, especially for extreme dynamic environments. But even beyond, there are a lot of challenges that have not been solved in magnesium alloys. So the first, obviously, is just if you look at the crystal structure of magnesium, unlike a lot of metals like gold, silver, copper that appears in FCC or the cubic crystal structure, magnesium has this hexagonal crystal symmetry. Now, what is the consequence of that? A very uneven CRSS landscape that is sort of temperature sensitive, right? So you're really sort of playing with this uneven CRSS landscape when you're trying to design these materials. And this anisotropy sort of travels across different regimes and shows up whether you're in yield strength or different kinds of plasticity mechanisms. So anisotropy is a very strong concern when we think about designing magnesium alloys. What's the next big challenge? The next big challenge is just making these alloys stronger, right? One of the conventional ways to strengthen materials is through a process called aging, where you just take this metal and put it inside a furnace and heat it. And that's supposed to produce precipitates and make your material stronger. Here are examples of commercial aluminum alloys. You can see that when you age it, there's a tremendous increase in the strength. But for these commercial magnesium alloys, you can see that there's very little increase in the strength, right? And people have been hard at work, in trying to improve some of these materials. When people looked at aluminum alloys, steel was the standard. When people developed magnesium alloys, aluminum alloys are the standard. And aluminum alloys have been fairly well established and developed at this particular point. If you look at the aerospace industry, for example, aluminum alloys are widely used. And that's because the design in part has been easy because of the cubic crystal structure. But magnesium alloys have a lot of interesting scientific challenges. So strengthening response is very poor, right? So that's the second challenge. So in this MEDE consortium that Jin mentioned, one of our goals was, well, how do we look at this problem? And we wanted to really do this in a very fundamental fashion. So we said, let's not right away jump to commercial alloys, but really focus on binary alloys. So we started with these three binary alloys of magnesium, aluminum, magnesium, zinc, and magnesium, yttrium. And the idea here was we would alloy this magnesium alloy with a small amount of this alloying element, such that the resulting precipitate or the intermetallic that forms when you mix these two elements forms precipitates along different habit planes, right? So for example, magnesium, aluminum would form these basal precipitates, zinc would form C-axis, and magnesium, yttrium would form these prismatic plates, right? And you can immediately see, just in terms of precipitation strengthening, that the systems are going to give you a little bit different strengthening, depending on how many precipitates there are and so on and so forth, right? And briefly, if someone is interested in some of these phase transformation pathways, I list them here. And especially for the magnesium, zinc, and magnesium, yttrium, you can see that they're fairly complex, even beyond what I've listed here. And I'll talk about that in a little bit. Okay, so to kind of keep this talk quite simple, I'm going to focus on one microstructural aspect, but in our consortium, we focus on a number of microstructural aspects, but I'm going to try to convince you why nanoscale precipitates are so important in the design of magnesium alloys, right? So let's go back to those three systems that I showed you. You can sort of develop this R1 increment and yield stress equations for all of these three systems, right? Which are a function of how these precipitates are oriented, how close they are, what is the sort of the mean distance between them, and so on and so forth, right? And really plot some of these equations, to try to get some design perspectives, right? So here is an example of R1 strengthening and effective, interparticle spacing. So let me focus on this graph on the right here first. What it tells me is that if I increase the number density of particles, the effective spacing is going to decrease. Very obvious, right? But if you think about which system is more effective, you can see here that for a given number density, prismatic plate is obviously the most effective one. It kind of makes sense, right? When you have a hexagonal crystal symmetry and you have basals there, right? Anything that is perpendicular to the basal plane is going to be very effective. So think about the example of a water flowing, right? And you want to stop the water flow with a plate. Would you rather have the plate horizontal to the water flow or perpendicular to the water flow? That's exactly what's happening here. So all of this, simple mechanics tells us that prismatic system is better than C-axis, better than basal, right? So if you look at it from the chemistry, what it tells you is that putting yttrium or maybe zinc is the most effective one. But it turns out that yttrium, or usually when you add a lot of rare earth elements, that's when you get these prismatic plates. And rare earth elements are very expensive and they're not widely available. Rare earth elements are not rare, but they're just geographically restricted. They're abundantly found in China, Australia, but not so much in US and a lot of other countries, right? And when you're trying to build, materials, for, in a very large amount, which is often the case for structural materials, you want to pick elements that are widely available in the Earth's crust. So my talk is now going to focus just on these two systems, just because of this logistical burden. Okay, and in particular, I'm going to refer to some of these alloys through these shortcut names. So when I say A6, what it really means is there's 6% aluminum in the magnesium, 9% aluminum in the magnesium, and Z3 means 3% zinc in magnesium, and so on and so forth, right? So these are some specific binary alloy chemistries that we have picked, right? So I'm going to show you just 3 recipes, and just so you know, there are a dozen recipes that have been followed in the MEDE consortium, but due to the paucity of time, I'm just going to focus on just few recipes to give you some broad level highlights of some of our work. So the way I'm going to kind of talk about design recipes is I'm going to start off with an argument saying, if I do certain thermomechanical processing, it's going to boost the strength in magnesium alloys. And I'm going to give you evidence to back up that particular argument, or maybe go against that argument. And finally, we'll ask the question of preponderance. Is this sufficient, right? And I'll give you a few examples, and it'll be very clear how this framework is used. So let's start with a very conventional design recipe, right? That's followed for a lot of metallic alloys. Take a piece of the metal and put it inside the furnace. This is what is called as a peak aging, or a conventional aging. And the question is, do we get very strong materials, right? Just by heating the material. So it turns out that when you heat this particular binary alloy, especially magnesium aluminum alloy, as I said, you get really elongated basal particles like this. You can see here these are experimental TM graphs that I've taken. If you want to get some insights into how these structures look, this is how the perspective view would look, this is how the top view would look, and this is the side view, right? The important thing here to notice is that all of these particles are fairly the same length, but when you look at it from the side view, you can see that due to the projection, they appear different lengths. And I wanted to show you this just to kind of explain some of the images that I'm going to show you later in the talk. So if I were to rotate this a bit, you can see that it matches with the experimental figure, right? So when I show you a figure like this, what I really want you to be thinking about is really a structure like this, right? So these are essentially particles that are sitting on the basal plane, and they're all parallel to the basal plane, right? Now, the first thing you can do is you can do these hardness measurements in quasi-static strain rates. And one of the immediate things that becomes very obvious is that these large particles that are very fast spaced offer very little quasi-static strength, right? So that's really a bad thing. So we also can do these experiments at very high strain rates. We have done Paul experiments. And one of the interesting things you find here is that traditionally, when you put more precipitants, your material is supposed to get stronger, but you can see that there's an inverse trend here, right? Where the solutionized sample, which has no precipitants, is much stronger in SPAL, where this is basically the strength at very high strain rates, but when you put particles, the strength goes down. And I worked with this, with a collaborator of mine, Dave Malik, who is at Army Research Lab, and some of his simulations show that these particles are essentially sources for void nucleated SPAL failure, and that's why you're getting lower SPAL strength, right? This is a perfect example of how the materials design principle for quasi-static applications cannot just be directly translated to high strain rate applications, right? So that's one of the reasons why nano precipitates or nanoscale precipitates are very, very important, right? As opposed to these conventional elongated particles that you get in magnesium alloys. So far we are getting some of these long elongated particles. And in terms of preponderance, it gives you poor quasi-static properties, poor dynamic properties. So in some sense, this preponderance fails. So we need to think about something else that can make this preponderance a success. So one thing to note here is there was no deformation given during the processing. There was just heating. And you'll soon realize why that's a very important distinction to have. A sort of an interlude here is that if you look at commercial aluminum alloys, this is in fact an aluminum alloy that's taken from an aircraft wing, and you have done TM on it, and you can see that the scale bars here are similar, and you can see how dense these nanoprecipitates are. But if you look at the same, magnesium alloy, in contrast, you can see how large these particles are. And a big question for the community for several decades, in fact, has been, how do we mimic the success of aluminum alloys and sort of make this in magnesium alloy as well? And people have looked at this, for example, almost 50 years ago, where they really tried to say, okay, can we accelerate this precipitation through deformation during the processing? So let's inject vacancies and dislocations during processing. So J.B. Clark, a famous scientist, did this tension experiments where he strained it up to almost 4% at a certain temperature. And the idea here was that when you inject these dislocations, they serve as nucleation sites for these particles. But what he found was that the sample obviously failed in tension, but also that the precipitates that were produced were just not sufficient to boost the strength significantly, right? So that's what sort of led us to sort of design recipe 2, where we sort of use this process called as ECAE, which is equal channel angular extrusion process, right? And this is a system here. And I'm not going to explain to you in detail what the various parts are, but in a very simplistic fashion, what it is basically you're forcing this metal sample, to go through this die, which has a 90-degree bend here. And you can do this multiple times because the shape is preserved. And at this juncture here, the 45 degrees, you're giving a lot of shear deformation to the sample, right? Almost close to 100% every strain cycle, right? Every pass. So we wanted to figure out, well, by injecting a lot of dislocations during this extrusion process, can we produce more precipitates? And in fact, some of our initial results really excited us, and we could see that indeed we were producing a lot of these fine nanoscale precipitates. But lo and behold, we were also producing a lot of these recrystallization bands. So we were producing almost a bimodal microstructure. I've presented here some nano indentation hardness values, and you can see here that in the grain interior, you have a certain hardness of almost around 1.5 gigapascals, but it's almost around 2.5 gigapascals in the grain boundary. And when you compare it to the conventional sample without any extrusion, it's definitely much harder, but it's a bimodal sort of a hardness distribution, right? But more importantly, we wanted to figure out, well, to what level were these nanoscale precipitates being produced? So this extrusion study was compared to the sort of the conventional study, and you can see that definitely there's an improvement in the spacing and the aspect ratio. So we were obviously changing the microstructure and producing some of these far from equilibrium microstructures, and really allowing sort of nucleation kinetics to take over the microstructure evolution, right? And obviously you can see that some of these dislocations are also participating in some of the nucleation events. And we kind of looked at this very carefully, and this work has been published in both ACTA and a few other papers, where we showed that this dislocation was essentially gathering some of these solute atoms, and that was reducing the nucleation barrier, and subsequently it was making it easier for the precipitation to occur. We've done this for several chemistries, and you can see here how, in the PKG, you get these very long particles, but in the extrusion process, you get these very fine particles, right? And you can see here, let me give you just one small example. Here is the A6 alloy. It takes almost around 20 days. This is the aging time in the log scale, and you get this much amount of hardness, which is quite low. But with the extrusion, it just takes 6 hours as opposed to 20 days, and you get a tremendous boost in the hardness, right? This is really kind of very interesting perspective, right? You're using those defects that are often produced during these extreme events, but you're using them, during processing in a way to kind of really produce novel microstructures that can in turn then again produce, really good performance in extreme environments. And we have done this for the magnesium zinc alloys, and we have produced some very fine nanoscale precipitates. And it's not just about giving deformation and temperature at the same time. It's really about optimizing it. And that's one of the biggest lessons we have learned during this particular process. So in terms of kind of summarizing this design recipe, the multiple passes of extrusion really produce this bimodal structure of nanoprecipitates and recrystallized zone. And it sort of gave us composite quasi-static properties and very poor dynamic properties, right, which are still sort of ongoing. And so in some sense, this preponderance fits, right? And one thing to note here is during the processing, we were getting significant amount of deformation during the processing itself, right? So I want to show you the design recipe that was really successful, where we really tried to control extrusion and then annealing, really to sort of rather scale back deformation and really produce very fine nanoscale precipitates. And the idea here was, let's try to kind of optimize annealing and extrusion and annealing and try to figure out which sequence is the best. And it turns out that the sequence where you do extrusion and then annealing is very favorable, because obviously you're injecting a lot of defects and vacancies, and that's sort of helping you with the clustering process. And through our collaboration with our Japanese group at NIMS, Sasaki and Hono's group, we have been able to show through atom probe tomography how some of these solute clusters look. So some of these mist-like particles that you're seeing are atoms, and these are all solute clusters. And if you look at the scale bar, they're very fine, right? So it's really exciting results. And these novel microstructures are being investigated at extreme strain rates, and we have some really interesting results that we're waiting to publish. So in some sense, this final design recipe sort of works, which is really exciting, right? Where you have these nanoscale precipitates. So I want to kind of quickly conclude how magnesium alloys are very useful. I just focused on strength, but it turns out that a lot of these nanoprecipitates are very useful for modulating yield asymmetry and other things. And I can talk more about that later on. But in terms of summarizing different recipes here, I've sort of really kind of distilled down some of the key lessons from each design recipe. And I did not mention one design recipe, which was important, where we actually really scale back the deformation to a very small value of around 10%, and to really see how the precipitates work. And here on the right, what you can see here is U stands for uniform and NU stands for non-uniform. So we went from this design recipe, which was very conventional, where we were getting uniform, large particles, and we really developed a final recipe that gave us uniform nanoscale precipitates, right? So that's really the benefit of that. So where next? In our Mechanics of Materials article recently, we summarized a lot of our experiments, but if you really want to push the next generation of magnesium alloys, we need a lot more experiments and a lot more data. And more importantly, we need a better integration between crystal plasticity models and precipitation and recrystallization phenomena, sort of thermomechanics that can guide us for materials design. And this has been a wonderful collaboration with Dennis and Yannick over at UT Zurich. So in terms of accelerating materials by design, the way it's usually done is we make some materials, we characterize it, we test its mechanical properties at different strain rates. But really for the future, can we do it in a sort of an inverse fashion where for a given property, we know how to design these materials, right? A framework that tells us what my processing parameters should be, what temperature, what strain rate, what strain level, what kind of a processing technique. And to get there, we really need high throughput experiments and also a lot of materials informatics work. So one of the things that I'm currently working on is sort of this informatics effort to gather a lot of useful values across both the experimental and computational space. And this has been a really exciting avenue. So with that, I would like to end my talk and really thank a number of collaborators, especially from Caltech, ETH Zurich, and NIMS, who have been really helpful for us. You can see some of them are here in this picture, and also the next speaker here, Suraj. With that, I would like to end my talk. Thank you so much for your attention.